In this video, we'll go through a teacher-led example of the t-test for two independent samples. So please have your practice problem set number 1 from chapter 10 handy and go through number 6 with me as I do the calculations. So hopefully this should look familiar. We've done these steps for the hypothesis testing before, and so we'll continue on with these throughout the semester. So first we need to state a hypothesis, then we need to select our alpha level, then we'll locate our critical region, we'll collect our data and compute the t-statistic, and then we will make a decision. Again, we're doing a independent measures hypothesis test or a t-test for two independent samples. So we're using data from two separate samples to determine if there's a significant mean difference between the two populations or the two treatment groups. And again, keep in mind on your test, you're going to have to be able to know by looking at an example, are we comparing two samples or are we having one sample comparing to a population mean? Because the calculations, as we've seen, are different. First, we need to state the hypothesis and select an alpha level. If this study states, a researcher wants to study the effectiveness of a new job skills training program for people who have not been able to hold a job. 14 people who have not been able to hold a job agree to be in the study. The researcher randomly picks 6 of these individuals to put through specific training, and the other 8 volunteers are put through ordinary training. So in terms of our hypothesis, we need to state what this hypothesis would be. And remember now, we have two populations that we're comparing because of that we pulled 2 samples from. We have population 1, and we have population 2. Now we're starting off with a two-tailed test, so it's non-directional. So we want to say that the difference between these two groups in our null hypothesis, there would be none, right? It would be equal to 0 because these two means would be the same. So the alternative hypothesis is that mu1 equals mu2, mu1 minus mu2 equals 0. There will be no difference between the groups. Our alternative hypothesis is that the difference between the means will not equal 0. So here again, the difference between the mean equals 0 because these two population means are the same. Down here, they're not the same. There's a difference between these two population means. That's our alternative hypothesis. So the difference will not equal 0, saying that there is a difference between the groups. And our alpha is set at 0.05. Okay, so now we need to locate the critical region. So if we go back to our example, we see that the specific training has an N of 6, and the ordinary training has an N of 8. So we'll put that here. So we calculate our degrees of freedom, which is N minus 1. That gives us 6 minus 1 and 8 minus 1, which is going to give us 5 and 7. If we add those together, that gives us degrees of freedom equals 12, and that's what we need to go to that table and find our critical T. So now we need to locate the critical region. So we use our degrees of freedom. We said our degrees of freedom was 12. So if we go across from degrees of freedom of 12, and we look in the column for 0.05 and 2 tails, that gives us a critical T of 2.179. So it's time for a short break. Okay? Take a deep breath. What's the difference between the independent measures t-test and a single sample t-test so far? We had a difference in our hypotheses. Because with the one sample t-test, we're saying that the sample either equals or doesn't equal the population mean. Now, in an independent measures t-test, we're saying that the difference in the sample means is either going to be equal to 0 or not equal to 0. Because the alternative says that there is a difference in those sample means, and the alternative says there's not. We've also seen differences in degrees of freedom because now we have 2 samples, so we have to account for the degrees of freedom in both samples. Okay, so here I just kind of made it more straightforward and simple in terms of what the data is. Now, the data wasn't in that example to begin with, the example that I had written out, but I did add it into your practice problem sets because I realized that it was just here in this table. So you notice that subjects in the special program, they each have a score now that they've gone through that program, and those in the ordinary group also have an individual score here. So also notice that there's 6 individuals in the special program group, which is why we have an N of 6, right? And here, there are 8 different individuals. Each subject has their own participant number, 1, 2, 3, 4, 5, 6. And now we continue on with 7, 8, 9, 10, 11, 2 through 14 to show you that these are different individuals in the 2 groups. So what do we need to do first with this data? In order to compute this statistic, we need to have our sum of squared deviations, we need to have our, which will ultimately give us our variance, and then our estimated standard error. We need to know our means. There's a lot of information we need to know. So go ahead and take some time to calculate those, the sum of x, and then the sum of x squared. So you take here, you'd have your x values, right? Now you need to have x squared. These are, oops, not there. These are your x values, and you need to get x squared. And then you need to sum them up. So we get a sum of x, and a sum of x squared here, and a sum of x, and a sum of x squared here. And voila. So hopefully you took some time to do that on your own. It's good practice for you. So the sum of x is 36. All I did was add these scores together to give me 36. I squared these values. So 4 squared is 16, 9 squared is 81. That gave me the sum of x squared of 240. I took this sum of x, I took the sum of x, 36, and I divided by 6 to get my mean. Same thing over here. I took the sum of x, divided by 8, mean. Now we need to compute the t-statistic. We already collected the data on the previous slide. So we need to get our SS for sample 1. And those values from the previous slide was the sum of x squared was 240 minus 36 was my sum of x, and I'm going to square that. I need to put that over my n, which was 6. That's going to give me 240 minus 1296, 6, gives me 240 minus 216, which ultimately gives me 24. So my SS for sample 1 is 24. SS for sample 2, if I pull the numbers from the previous slide, I get my sum of x squared was 98 minus sum of x. I'm going to square that, and I'm going to put that over my n, which was 8. That gives me 8 minus, which gives me 98 minus 576 over 8, which gives me 98 minus 72, which gives me 26. Next, we need to get our pooled variance. So we're going to take our SS for sample 1, which was 24, plus our SS from sample 2, which was 26. And we're going to put that over the degrees of freedom. So we said our n for sample 1 was 6, and our n for sample 2 was 8. It gives me degrees of freedom of 5 and degrees of freedom of 7. So we put that 5 plus 7 here, and we calculate this. I'm going to erase this real quick so we have some more room. over 12. And our pooled variance then is 4.167. So now we need to calculate our estimated standard error. So if our pooled variance, so remember that P stands for pooled, and this S squared is our variance, 4.167. So to calculate our estimated standard error, we need the square root of 4.167 over 6 plus 4.167 over 8. That's going to give me square root of 0.6945 plus 0.5209, which gives me the square root of 1.215, which ultimately equals 1.102. So this is my estimated standard error. I put that into my t-statistic, and if you go back and look at the previous examples, we know that the mean of sample 1 is 6, the mean of sample 2 is 3. That's our sample means, right? M1 minus M2. We know that our expected difference between population mean 1 and mean 2 would be 0 over 1.102. Ultimately gives us 3 over 1.102, or 2.722. So now we need to make a decision. So we had said that our critical t was 2.179. Our calculated t from the last slide was 2.722. So our critical t is 2.179. This would be a negative, a positive 2.179. Calculated t of 2.722, it falls out here. So it's in that critical region, so we reject the null hypothesis. The new Special Job Skills program is significantly more effective than the ordinary job skills training program. Or, since we're talking in just a two-tailed test, the new Special Jobs Skills Training Program produced significantly different scores than the ordinary job skills training program. And then this is how we report our t-statistic. This is our degrees of freedom. This is our calculated t. And this is our p-value. This is our alpha. But we report it as a probability is less than 0.05.